All attendees are in listen-only mode.
Hello everyone, can you hear me? Great. Okay, so today we'll be talking about catapults. Did you all get your catapult kit in the mail? Gabe, you didn't get it? Okay. Snowing. Okay. I'll let Mr. Dubik know, but make sure that it's not something on his end. But okay. I'm glad the rest of you got it. Did you get a snow day? Left midday. All right. It's a half a day, I guess. Okay, cool. Well, I got my kit. It's pretty cool. I haven't glued it or anything, but I think you guys will be pretty excited about it. If we have time at the end, I'll send you a screenshot of what it looks like, Gabe, so you can at least anticipate a little bit more. Building the catapult. I think we're going to talk more about building the catapult in another class, but we're going to talk right now about how, the mechanics behind it. The instructions are definitely kind of vague. I think I can definitely help you out, and I haven't actually put it together yet either. I did, put some pieces together, and I ended up with one very big extra piece. So I'm not sure. I'm gonna have to do some more work on that too. But we don't have to actually put it together yet. If you want to go for it, go for it. But like I said, next time. So I'm pretty sure. One sec. I might have pulled down the wrong. This is okay. Yeah. Maybe this is gonna. Yeah. Okay. This is for us. Can you see my screen? Oh, sorry about that. Okay, I'm talking and you have no idea what I'm talking about. Here we go. Okay. So, let's get to, all right. This has materials needed for today. You don't need those today. This is for that slide's for the people who are taking this course in class, but really, this is just showing you how to make it. I hope you all know what a catapult is. Basically, it flings something solid, something big and heavy into the air, and sometimes it's on fire, sometimes the slide says mainly to inflict damage. I think often, rather than damage being soldiers on the ground, often it's maybe throwing balls to knock down a wall or something, but there's a lot of different categories. Those being the traditional catapult, the Ballista, and the trebuchet. So this is the trebuchet, traditional catapult. Basically a bucket arm is held down by tension. Here you can't really see it, but there's one string. I mean, you can see this. You can see the string holding holding this arm, holding the spoon and the eating end of the spoon, I guess, if you want to talk about it that way. It's holding that down, and the end of the spoon here is under tension. I think that what they have done is stick it in. Oh, they haven't put tension on it yet. That's these. It kind of looks like antlers, but when it's fully extended, that would get really tense and fling it forward. So this is what we'll be making. So there's the arm. Yeah, that what I said about this was wrong. This is not a very clear picture. So this is a better picture on how this catapult actually works. So to release a lot of energy really quickly, there has to be some way to store it first. And to do that with the traditional catapult, it takes some wound up string, and you insert the pin. In this case, the pin is the arm of the catapult inside of that string and twist. And that obviously, if the ropes has been wound around tight enough, then it doesn't want to unwind, and it when you release the catapult, it will twist itself back. As it says here, it's stored tension by twisting and stretching ropes or bending wood. Occasionally, it's more of a bow and arrow sort of thing, but this is the more typical traditional catapult. So you see here, this is a bow and arrow, not a catapult, but it's similar how you're storing the energy as potential energy in the bending of here it says stored in a bowstring. It's actually stored in the I don't know what you call it, the hilt or the wood of the bow, that long arch. That's where the wood really wants to resist bending. So when you pull back the shaft, thanks Gabe, when you pull back on the bowstring, the shaft wants to resist that, and you're adding potential energy to the shaft. And as soon as you let go, that potential energy is released and transferred straight into the arrow. So we'll see how that is fairly similar in the catapult. The traditional catapult can store more energy to send their projectile further by using a winch. So if you notice, well, we'll ignore the tension in the yeah. So can one of you tell me? Can one of you tell me what they added to the catapult here, to this winch? What simple machine did they add to make it easier to store energy? Can you guys tell? A lever? So Gabe says they added the lever, but in fact, actually, that lever arm was there in the traditional catapult. A pulley? That's close. I think you might be confusing that with the line that the winch is pointing. That's really just a line they added. Jaden says gears, and Kevin says an axle, and that's really getting close. So it's the oh, now I'm drawing a blank. It is the axle, but what's that paired with? The wheel and axle. Yes, thank you, Kayla. That's right. So what they did was they added a wheel and axle, and that let them use a lot more movement to really tighten down. So they can turn, you can see how this wheel turns a lot further. This guy turning this wheel, his arms do a lot more movement, which transfers to a very small rotation in this in the winch on the axle, and so that allows them to put a lot more tension in the arm because he doesn't have to be quite as strong. He's reducing the amount of force to turn it, and actually he's not actually less strong. It just lets him use the same amount of force, but store more force in the arm because they make the arm that much harder to turn, to pull back. So that's how this winch adds power. Does that make sense? Yeah? Okay. Cool. Let's see. So we talked about this. It allows a person to store a great amount of energy over a period of time. So basically, it goes back to what we've been talking about this whole time about if you add, to accomplish some certain amount of work, you can either change the distance or change the force. And so in this case, they kept the force the same because the guy's just as strong, but they increased the distance, so they were able to make a better catapult because if you keep the same force and a bigger distance, what does that mean? To work. Does work go up or down if you have the same amount of force but you're using a longer distance? Kevin says down. Kayla says more work. Yes, you're right, Kayla. So if you're not reducing, we said work equals force times distance. And if force is the same and distance is going up, then you're able to do more work. And what that means for this catapult is it releases more energy. You've done more work to the catapult in tightening the tension, and when that's all released all at once, it has more energy to throw back at the ball, which means the catapult shoots further. So here we see another type of war instrument, the Ballista, that is, I guess it's an advanced bow and arrow or crossbow that is made to shoot even bigger shafts. Yeah, it says here, it looks like a giant crossbow, because that's exactly what it is. It uses gears you rotate it back along a train. Let's see if we get a better picture. It still uses tension stored in string and wood, like they said, like the bucket catapult, but it's similar to a bow and arrow. It says there is additional energy stored in twisted ropes. Let's see if we can explain that further. Okay, I don't exactly know how the ballista works. I'm sorry. It's not very clear from this picture, but I do know that to tighten the ballista, it's really hard to see, but right in here, it kind of blends in, but this shaft right here at the end, there's two sticks that are twisted, and that makes that's a wheel and axle right there. So you push on the outside of these sticks, and that turns the axle in the middle, and that allows you to add more tension to these ropes that tighten back. Oh, and they said it's stored in the twisted ropes. That's in the same way. That's at the front here. It's kind of like the catapult is twisting in ropes, and that's providing the tension. Up at the front here, both of these sticks are stuck between really, really tight ropes, and so as you pull them back, those ropes resist that movement and want to straighten back out, and that's where the tension comes from. But the big improvement was taking the bow and arrow and adding the wheel and axle. So we'll see this theme of more, and I mean they just keep adding one little simple machine to a previously existing technology, and they are able to add a lot more power. Oh, I'm sorry about this. My sound. Oh, I apologize. Okay. Let's see if I can silence my phone. Okay. You're able to, what they're doing here is taking previously, there's a technology that's existed for often thousands of years, and they add one little simple machine to make it maybe, I guess it's a complex machine, but you add one simple machine to that complex machine or system, and you just get incremental improvements to get more and more power or efficiency, or you can get a lot more creative uses out of it. So, the history of catapults. We have limitations as humans. We can only lift so much or throw so high, but we have the advantage of being able to store energy in projectiles. This is, this. We've already talked about this. So by storing energy, you can increase the amount of damage. Not just damage, though. With catapults, yes, but you can also do a lot more cool things. We'll get to that later. So war has often been the motivating force, which has helped advance engineering in many other ways, not just weaponry. We saw a little bit of that last time. Here, well, let's get into some details. So I think what the goal of this is to be able to calculate the in learning gravitational potential energy, the goal of this is to learn how to calculate how much energy you can transfer into a catapult or something like that, and how to measure that and that sort of thing. Jaden says, like throwing Limburger cheese at the bad guys. I'm not sure how that relates to gravitational potential energy, but is that a Monty Python reference? That sounds like a Monty Python reference to me. I'm not sure. Okay, so no, it's to use as a catapult. Okay, I see. All right, so the gravitational potential energy of an object can be found by multiplying the weight of the object by how high it is off the ground. Specifically, well, no, yeah, I guess that's right. So all you need to know is how heavy the object is and how high it is, and the Earth's acceleration due to gravity, which is a constant, but the equation changes if you're on the moon or on Mars. You're going to use a different gravitational constant. So it's actually, this is wrong, it's weight times height times 9.6, or we can, as engineers, we like rounding, we like just making it easy and using 10. I mean 9.8 I meant, but really 10. So weight times height times 10 meters per second squared down is the acceleration due to gravity. And that gives you units of energy. So as long as you keep your units consistent, then you get a normal measurement of gravitational potential energy. So what does that mean? That is like saying when you throw the ball at well, so when this catapult is twisted back, it has potential energy which means this is how much energy is stored in the strings of the catapult, so that when that energy is released and transferred into the ball, assuming 100% of the energy is transferred into the ball, then that ball that's thrown will gain kinetic energy. And then if that ball were thrown straight up in the air, then at some point it would stop moving entirely. It would just stay for an instant. It'd be right up in the air, and it'd have 100% potential energy because it's not moving. So the gravitational potential energy, 100% gravitational potential energy at the top of its peak. That means it's not moving, but because it is high off the Earth and the Earth pulls things towards it, it wants to fall back to the Earth due to gravity, and so you can find like the maximum amount of energy transferred into the ball by taking the weight of the ball times its height times the acceleration due to gravity at the top. I think we'll get into more of this later, but this is just to get you used to the idea of thinking in terms of gravitational potential energy versus kinetic energy, which is the movement of the ball, and versus well, do you know what kind of energy it would be called when it's stored in the strings of the catapult? This is a tough question. Potential, Gabe says. That's right. And it's not gravitational potential energy, though, because it's not due to the Earth's gravity that it's got potential energy. It's the exact term is escaping me, but it's something like molecular potential energy, but mechanical potential energy, maybe? Yeah, mechanical potential energy. So that means something in, like, the strings are being pulled really tightly, and so it's mechanical potential energy is the category of potential energy, storing energy in a way that is mechanical. It will it's under tension, I guess, in this case. I'll look up that term too, because something about that doesn't sound right to me. I think I'm making okay. Anyways, it's a different form of potential energy, but you're right, Gabe. It's potential energy, not kinetic energy, because once you've wound all that energy up and you've tightened those, the catapult's all the way tight and just about to be released, but nothing's moving. So there cannot be any kinetic energy in this system. So how do we increase the potential energy? We have two options. We can make the projectile, put more energy into the projectile to throw it higher off the ground, or to make the projectile heavier. That follows from this, the fact that you can increase weight or you can increase height to increase the amount of potential energy that you can put into it. I know that might not be it might be a little unclear, because this is gravitational energy, and we're actually adding in some mechanical potential energy in the strings. But at some point, all of the energy equations are very closely related. So kinetic energy is also dependent on weight, and similar units like weight and speed. Here, height well, there's a relationship between the weight of the object and the energy that you put into it, and that's has to do with the energy. So really, it's the mass, not the weight, because more mass has more energy and more potential energy. Getting more energy into it obviously increases the potential energy. Basically, that's what you're doing when you throw it harder. Oh, here we go. This is what I get for not reading the lecture ahead of time. It's not mechanical potential energy. It's elastic potential energy. I think elastic is a form of mechanical potential energy, but that's the correct word. So I'm going to say this to clarify. You're putting in elastic potential energy. You're storing everything. Your catapult is storing in elastic potential energy. As soon as you release it, it launches it, and it's throws the catapult immediately as kinetic potential energy. As soon as the catapult leaves, it's all kinetic potential energy. And then as soon as it gets up into the air, if it went straight up into the air and paused and then fell back to the ground, then that would be bad because the ball would land on the catapult, and then crush the machine. But that would be 100% if it actually pauses in the air. Usually, the ball, you don't want that to happen. You don't want to ruin your beautiful machine catapult thing. So you want to launch it sideways, and so it's always moving in the air, so it actually never reaches 100% gravitational potential energy, but at some point it comes to a maximum potential energy when it stops gaining in height and it starts falling. So from elastic to all kinetic to some mixture up to a maximum of gravitational potential energy and a little bit of kinetic because it's still moving forwards, and then it's right the instant before it hits something and crashes, it's 100% kinetic energy again, right? Well, yeah, kinetic energy. Gabe, I think you're thinking of that movie that had a lot of problems with it. I can't remember the name of it. 100% of their brain and are able to control the energies in their body. So you can transfer that energy into a new form. I mean, theoretically, if you could use 100% of the energy in your bodies, your brain could control that, you could certainly do a lot of things, but your brain doesn't have the mechanisms in place to actually do that. So unfortunately, that's a little tricky. But if you want to invent the device or figure out how to meditate so that you can actually use all of your energy, go for it. I'm not going to stop you. Electroshock. I don't know about electroshock therapy. I don't even know. That sounds dangerous to me. But we'll keep going. So, yeah, we talked about this. Engineers researched ways to increase their energy storage in weapons. In around 400 BC, Dionysius of Syracuse, not in New York, I believe this was in Rome against Carthage, created a think tank to design and build weapons, trying to overcome limitations. So we saw some examples of how they were able to do this. You have a couple of factors you're able to control. Let's see. Angle and power. So what affects elastic potential energy? Angle or power? What do you guys think? Angle, Gabe says. Do you guys agree? Kayla says power. Jaden or Kevin, we need a tiebreaker. Kevin says power. The majority wins. So it doesn't matter what angle you hold your bow at, because the elastic potential energy is how much energy you're pulling back and putting in the strings. No matter what angle or position, you could be pointing it straight at the ground or straight in the air. As long as you pull it the same amount, you're putting in the same amount of elastic potential energy. So now what Gabe might have been thinking was gravitational potential energy, which would certainly be affected by angle, because if you shot it straight up in the air, then at some point it would become 100% gravitational potential energy because it stopped moving. Or if you shot it parallel to the ground, then you're not really ever adding gravitational potential energy. It's just going to fall, and I guess it had a little bit of gravitational potential energy because you shot it above the level of the ground, and it falls into the ground, and so it loses a little bit. But anyways, a bow experiences compression on its concave. Yeah, okay. Here, this slide just shows you how the bow, on the inside it experiences compression, and on the outside it experiences tension. So often those materials that you want to use, tension is a pulling or stretching force, to be clear. Compression is pushing. So when you're when you put your TV on top of your TV stand, your TV is adding a compressive force to that TV stand. When you pull on a rope, you add tension to the rope. So tension is really about pulling things apart, and compression is all about pushing things together. So if you think about a lot of common materials, they usually have, they vary. They're not usually the same. They're usually not so good at. They're usually good at one or the other, or maybe okay at both, but not great. For example, a rope is really, really great at tension. You can pull a rope really hard and it won't break. But if you try to stand your TV on a rope, what's going to happen? It's going to fall straight to the ground, and it's just not built for compression. Whereas another example would be concrete. Concrete or asphalt, they're built to have things, press them into the ground over and over and over repeatedly and not break. It's obviously not easy because they have to send people to go out and repair the roads, but they do a pretty good job, much better than if they were to, use other materials. Asphalt and concrete are particularly good at compression, and that's why we add them that's why we use them as road building materials rather than other structural materials. Now, you might be thinking, well, you put a lot of concrete in buildings, so why am I? Maybe this isn't the greatest example, but buildings have to stand up under their own weight and hold the roof on top and all of the materials inside. So that's a lot of compressive forces. But concrete alone is not necessarily a great. Buildings undergo both tension and compression. If winds blow against them, or certain beams are under tension, or different areas of the wall might be under tension. Exactly, Gabe's got it. So you add rebar and steel beams, which are excellent at tension, and depending on how you construct them, they can be good at compression, but they're expensive, so you don't want to use a lot of them. Concrete's cheap. So you use concrete for compression, and you put rebar or steel beams inside of it, and that helps them reduce the tension inside of them. And you can make much thinner walls than, you saw how the Romans built the Colosseum using only concrete. Well, those walls are really, really thick, and that's because they didn't have rebar, and so they had to make the walls so thick that they wouldn't buckle under the tension of different forces that are. It's hard for me to explain how they might be under tension, but archways and that sort of thing. There are a lot of walls in general are under the most tension in the middle and under the compression, more compression at the ends. So they have to make the walls often especially thick in the middle, and then obviously if you add more thickness in the middle, you have to make more thickness at the bottom to support that extra weight of concrete, which is really heavy. So you get walls that are really thick at the bottom and go up to become more thin at the top, and that's why the Colosseum looks the way it does, because and they use really thick walls. Now, if they had rebar and steel beams to put inside of them, then the Colosseum would be much, much thinner because they wouldn't need to use as much concrete. They might have used some long wooden poles, Gabe. I am not aware of that, but I think that was just for like scaffolding to get up there, but maybe I'm wrong. Maybe I'm not sure. I thought that they only used, it was just concrete. Maybe they added rocks and things to inside the concrete and the mortar to take up more space and to make the concrete go further, but I don't know. Okay, so how do these forces store energy? Rubber band is a really good example to imagine this. So it's really about breaking down what's the difference between a loose rubber band and a tight rubber band. The potential energy is stored in the rubber band exactly the same way as when a bow is drawn or in the strings of a catapult. It's all in the forces. You really have to go down to the molecular level, because what you're doing is this rubber band is made of a plastic that when you stretch it really tight, when you stretch it, all of the little plastic molecules, which are really long and tangled up together, they get stretched out, and as they pull across, as they get stretched out, they really want to return back to their original position. So you can imagine if you have, it's kind of like stretchy elastic, or when you have a sewn shirt and you pull it apart, but it wants to pull back together. Those, you can imagine all of the little fibers in your shirt that when you pull it, when you stretch it out and it comes back to the way it was. Each one of those fibers was actually a molecule. That's what's happening in the rubber band, and so it's really the molecular attraction that pulls the rubber band back together. That's the exact same thing in all of this kind of potential energy, elastic potential energy. So the bow and arrows just take advantage of that by transferring the elastic energy in a very direct way. Whereas a rubber band, I guess you can make a bow and arrow out of a rubber band, but bow and arrow is just the way it's designed. The shape is designed to release the energy from at one specific point, and it does that well. So then, oh, okay, well, yeah, I think you get what I'm saying. So, if you like, you can build a double skewer bow with just using household items like tape, string, a wooden skewer or stick or whatever you find that's just a little bit bendy, and a pen. I think it's pretty clear from this picture. I can, let's see. I will send you guys this picture somehow. I'm going to ask Mr. Dubik how I can send you this picture, because I know it's easy to see exactly how it works, but if you want to make it, I think it'll help to refer back to this picture. So I'm going to write it down. Okay, I'll figure out how to send that to you guys. Jaden just shot a ball across the room with his catapult kit. Way to go, Jaden. That's awesome. I still have to get my glue. I wish I could say I could do the same, but that's really cool. I'm glad to know that it works. How far did it go? $10 to 12 feet. Awesome. Cool. Okay. That's about as big as long as my apartment. So I know this cool thing with a clothespin that makes it into a crossbow, Gabe says. Cool. Well, if you can find a link, you could share the link to a YouTube video or something that shows us how to do it. That'd be really cool. So let's keep going. Some safety. I guess Jaden missed the safety, but just good things to keep in mind, especially when you're building this, sort of thing. I know you're not using, well, for the double skewer bow, you might be using some scissors and that sort of thing. You might use glue. It's always a good idea to wear eye protection, no matter how it seems. Even if it seems like the most innocuous thing that Gabe, this is an important point, because if you use power tools, that's great, but you should always be using eye protection. And if you go to a college where you go into the mechanical engineering factory, you meant number 5. Ask for help for potentially harmful tools. Yes. Okay. So if you, yeah, I'll just continue that. Okay. So, as I was saying, if you go to college and you get into mechanical engineering, to the machine lab, they're not going to let you use any tools in the lab until you've been trained, and you always wear all of your eye protection and follow every safety procedure. And as soon as you don't follow safety guidelines, they're going to kick you out. And before they let you back in, they'll make you at least retake the safety course, because they'll assume that you weren't paying attention the first time. It's that important, and it's very important. So always wear eye protection. It says never substitute metal tableware for plastic. I'm not sure what it's referring to there. Maybe for the crossbow, never use metal tableware for replace. Oh, I see. Don't replace the plastic tip with a knife. Good call, Gabe. Yes, that's exactly what it's talking about. Okay. Don't launch at people, animals, or things of value. That makes sense. Obviously, things of value is less important than people and animals, but you'll just have to take responsibility if you shoot it at something of value, I guess. Or people or animals. You might have a lot more responsibility with that. But anyways, you get the point. And ask for help. Only use them at home, not in public. That's a bad idea. Yeah. Okay. If you've never used a tool before, ask for help. Never be afraid to ask. Okay. We're not going to build a double skewer bow right now, but you can. If you want to write down the supplies right now, go for it. That's great. I'll pause here, or if you want me to send you the list later, yeah, I'll just do that actually. Supplies list. Okay, I'll send you the supplies list later too. Jaden says he just shot the spoon off the catapult, hole in one to the trash can. Cool. I'm glad you're having fun with it. That's and Gabe, I know you're jealous of Jaden for having built his catapult already, but you'll have your fun soon. Soon enough. I bet it was in a triangle pattern. What do you mean, Gabe? In a triangle pattern? I don't know this Illuminati reference. Is this maybe there's some Dan Brown going on? I'm not sure, but anyways. So we'll cover quickly how to do this. So you open up your pen, disassemble it, pull off the little rear housing cap. If you need to, you can use some pliers to get a grip on it, especially if you don't have nails to get your finger in there. Cut the pen in half. Stick something into the, this is a little confusing here. It's really a lot easier than it looks. So get your skewers and stick as many skewers into the pen casing as you can, and tape that down so that the pen housing doesn't slide along the way. Then you want to tie your string, which is the hardest step. You put tape at the ends, and then or something that will keep the, a thick piece that will hold the string from sliding down the end, and then you want to make sure that your material will bend just enough that it will hold some tension. So yeah, just like that. It says this is a tough step. I've never done this before, so or it's been a while since I've done this. But apparently a pair of tweezers might help you grasp the string if you have a hard time. I don't think you should have a problem. The hardest part is tying it very tightly. But yeah, good luck. And fire. Don't forget to wear eye protection, and don't aim it at anything living. Clearly the two most important things. Okay. So, how does this work? We went over it. This is a little bit of a repeat, but it's all compression and tension. The bow is under compression and tension, which not the shaft, I already forgot. What's it called? The thing you hold. It well, I guess, let's see. The skewers. Okay, we'll call them skewers here. So the skewers are under compression on the inside and tension on the outside, and they don't like to be under compression or tension. They resist that, and they want to fling back. So that's called elastic potential energy when it's under compression or tension. It wants to snap back. So engineers tend to look at this as a force curve. Usually there's some length of displacement, which in this case is the length of the draw length of your arrow, and then on the y-axis is the amount of force your arm exerts. So as you continue to bend this back, you pull with harder and harder force, and you're storing more and more energy into the bow. Now, you can see the curve looks like this, and you'll notice that the units or what we're looking at here is the force and the length. Now we said that work equals force times length, and so if you multiply these two numbers together, you can see this becomes a square, and because it doesn't take very much force at the beginning, and because it's linear, you put very little force in at the beginning, and you put a lot more force in at the end. This is actually your force increases linearly with how much you pull the bow back, and so that means you end up dividing by 2 when you multiply. So you get force times length divided by 2, and that gives you the amount of work. The potential energy, not work, but work is a unit of energy, so that's where I was confusing you. But yeah, so this tells you how much stored energy is in here. It's the amount of area under the curve, which turns out to be the force times the length divided by 2. And that is the equation for potential energy: force times length over 2, or one of the many equations for potential energy, but that's the one that applies in this case. So if you pull the string back further, you increase the draw length. It increases linearly in this type of system where you're under tension, and you're adding elastic potential energy, and so you add more length equals more. You pull with more force, and it ends up storing more elastic energy. What happens if you shorten the string is shown here. If you have a pre-tensioned bowstring, because you shorten the string, then it reduces the distance that you actually end up pulling because it's already pre-tensioned. So your stored elastic energy just gets cut off, and you lose just this little tiny bit of energy right at the front between 0 and up to around almost 5. You didn't pull that amount of energy, so that was one of the modifications, because as humans we can only pull a bowstring back so far before our arm just doesn't want to pull back anymore. We can't physically pull it back anymore. So one improvement to just a bowstring they did, that early engineers made and designers, they pre-tensioned the bowstring so that it's already tight. And whereas if it were not tight and you pull it back, you have to pull it back further, and it's hard for us to get all the way back and add that energy, because we have, we only can pull so far. So if you pre-tension it, you don't have to pull that bowstring back so far, and you only lose the amount of energy that's at the very beginning here, between 0 and 5. So if it's pre-tensioned up to, where would that be? About 3 pounds of force, if you kind of extrapolate this line over. So that means that it's easier for the human body to pull it further, and you end up being able to store more energy because you're gaining on this bigger end where you're really storing a lot of energy at the end. So that gain is going to be really big just by pre-tensioning the bowstring. Let's look at other things. You can increase the stiffness of the wood. Now, what this does is it means if your wood is stiffer, then it's going to resist you pulling it more, right? So for every amount that you are able to pull it back, if you have the strength to pull it back, you can still pull the same distance, but with a much stiffer wood, it is a lot harder to pull back, but you can it'll hold a lot more force for that same distance we've been looking at. So this green line here was the pre-tension bow that let you pull the bow back a little bit further, but the stiffer bow, if you use pre-tension and stiffer, then that lets you store much more energy, almost twice as much. Gabe says it doesn't mean it's going to shoot harder. Well, if you're using just a stiffer bow and you're pulling it back further and you have a clean transfer of energy, then it will shoot harder. But you just have to assume, things like it doesn't break, and you can actually pull it back that far. You have to pull it the same amount of distance, remember. So you're actually, before you only had to pull it back to about 20 pounds of force, and now you have to pull it back to 40 pounds of force. So if you're strong enough to pull it back, then it will shoot harder because it's resisting that tension, and it's going to straighten back that much faster. Yes, we are just mentioning this. The bow has to be strong enough to carry the maximum pulling force without breaking. So what does this mean in terms of improving design? They discovered that if you make a compound bow, you can strengthen it, or a compound bow is a bow that's strengthened by combining wood with animal horns and animal sinews. So sinew is much better at tension. That's the things that connect your things like ligaments in your legs that are really good. Your muscles pull all your ligaments and they move your legs, and so the muscles are always pulling the ligaments, and that's what this animal sinew is. Those are the ligaments that are really good at pulling. Your body, the animal's body has made them to just exclusively to be really good at pulling. So when they put animal sinew on the outside of the bow, where we said the outside of the bow is under tension, if you put those sinews on the outside of the bow, then those are going to be better at tension. Then if you use wood or animal horn on the inside of the bow, those are generally much better at compression. And so you're able to use different materials on either sides that, okay, Jaden has to go. All right, that's all right. We're pretty much done. We probably come back here and continue this tomorrow. Oh, it's 7:58. Okay, yeah, I should let you guys go. But the gist is it holds up better to compression and tension, and it works. All right, see you, Jaden. We're going to end this in just a minute. Okay. Yeah, we'll end it right here, actually. Before we get to, I guess when we come back, unless Mr. Dubik tells me otherwise, we're going to build a compound ruler bow. Sometimes he tells me just go on to the next lecture. So I hope we get to continue back with this one tomorrow, but we'll see. Wednesday, sorry. But thank you guys for showing up, and I look forward to continuing next week, on Wednesday. Sorry, not next week, Wednesday. Okay. I hope you have a good night, too. Bye, guys.